All right, going to have your homework out if you would, please. Open on your desk. Books open as well at page 128. You had 4 questions to answer, questions 17 through 20, and also did 4 problems, problems 7, 9, 10, and 11. Let's start by going over the questions, though. Number 17 asks this: what are the 4 fundamental forces of nature? Audrey.
The 4 fundamental forces of nature are the strong force, electromagnetic force, weak force, and gravitational force.
Good, and that was in order of descending strength as well. Good. The strong, the electromagnetic, the weak, and the gravitational. Number 18, what is the difference between a geocentric solar system and a heliocentric solar system, other than the fact that geocentric doesn't exist? Other than that, though, Kendall?
The geocentric solar system has the Earth at the center of the solar system, while the heliocentric solar system has the sun in the center.
Very good. Number 19, what are Kepler's 3 laws of planetary motion? Michael?
Kepler's laws for planetary
Kepler's.
laws for planetary motion are the law of orbits, the law of areas, and the law of periods.
There we go. Those are the names of them. Doesn't say a whole lot about them, but it didn't ask what do they say. It just said what are the 3 laws. I can't fault you for putting the names of them. We'll talk about those later. And number 20, what does, and here we dive a little deeper, what does Kepler's 2nd law imply about the relationship between a planet's distance from the sun and that planet's speed, Audrey?
The farther away it is, the line lengthens and the base must shorten.
Okay, I see where you're going with that. Okay. Kendall, did you have something a little different, perhaps?
The closer to the sun a planet is, the faster the orbit.
There we go. The closer a planet is to the sun, the faster its orbiting speed will be. Not that you're wrong, it's just that kind of was used to lead to that ultimate point there. Good, let's go and review some things before we look at the problems. We talked about a famous scientist, and he came up with 3 laws of motion. Now, that differs from Kepler, who you read about in your homework reading, 3 laws of planetary motion. This guy was just 3 laws of regular motion. And who was that guy, class? Newton, Sir Isaac. And I guess that's how he signed his legal. Anyway, Sir Isaac Newton. And the first law is one we've talked about really since the beginning of the school year, Michael.
Law of inertia.
Law of inertia, which says what?
Anything moving at a constant pace unless acted upon by an outside force will not stop.
That was kind of rough. He got some of the right words in there. Audrey, can you help him?
Something at rest must stay at rest, and something moving will keep moving.
At a constant
Speed.
velocity or at a constant speed in the same direction, unless
Acted upon by an object.
an outside force. Okay, we don't know that as well as we thought. Okay, an object will maintain its velocity unless acted upon by an outside force. Again, that takes care of the rest, and it takes care of the moving, and it takes care of the straight line and constant speed, all that. An object will maintain its velocity unless acted upon by an outside force. That's the most concise way to say it. The second law basically was a formula, Kendall.
The force is, you want the formula.
Yeah.
F equals ma.
F equals ma, which basically says that the change in velocity when an outside force acts, or what is change in velocity, class? Acceleration. The acceleration of an object depends on 2 things. What are those 2 things, class? Force and mass. Acceleration depends on force, it depends on mass. More force, more acceleration. More mass, less acceleration. So directly proportional to force, inversely proportional to mass. And then the third law basically said what, Audrey? I go walking along the ground. And as long as there's some friction for my foot, the ground pushes me forward. If I push back hard, it pushes me forward hard. If I push back softly, it pushes back softly.
Everything is against you.
Well, not entirely true. Try again.
The force that you press upon an object is equal to the force the object presses back.
Yeah, there's a better way to put it, though.
Is it like equal and opposite reaction?
There we go. For every action, there's an equal and opposite reaction. There again, it doesn't always that, right? We talked about the pull downs, right? Or you know, any of you ever done that rope climb thing where rope hangs, so you climb up the rope as high as you can, as fast as you can, and till you can't keep going. Well, you're pulling down on the rope, correct? The rope pulls back up on you unless it's like been sawed through or something at the top by some jerk who knew you were going to be using that rope. And then you come tumbling down because you were expecting the rope to hold you up, right? You pull down, rope pulls up. That's why you go up. You're not pulling up, you're pulling down. It's the rope that's doing all the, okay, not really. But anyway, action reaction is basically the third law. So first law, inertia, everything keeps its velocity. Second law is all about acceleration, F equals ma. Third law, action reaction. For every action force, equal and opposite reaction force. Then we talked about, I mentioned a moment ago, friction. Now, everything's not against me, but friction always is. Now, against me can be a good thing, right? Especially we talked about the leather-soled shoes. I want friction to be against me. I need that help. But friction always works against. So we say that friction is a, what kind of force? It's always, it is always negative. That's true. Mathematically, it's always negative. There was a term I used in the definition. Friction is the resistive force that arises when? Anyone?
Pass through a master medium.
Well, yeah, we said kind of, yeah. We're not looking at it so much from that perspective of passing through a medium, but more sliding across a surface. When it slides across a surface. So there's that resistive force when an object slides across a surface before it goes through a medium, is friction. Talked about two types of friction. The one type of friction is a little bit greater, and it's the friction when you start trying to slide something. Class, that's called static friction, because the object desires inertia, intends to remain static, remain stationary. And so the static friction is a little bit stronger. Once you've got it moving, though, there's still this friction that has to be overcome continually, right? This is why if you're dragging an object across the floor, as soon as you stop dragging, it doesn't keep sliding, right? Not true necessarily of, for instance, if you were on like ice or something and you were dragging a box across the ice and you're dragging it, if you were to let go, it might actually keep sliding a little bit on ice if it was smooth enough. But on carpet, certainly, on a rougher surface, as soon as you stop pulling, it stops moving because there's that resistance. We call it resistance to continue or keep sliding. Kinetic friction. Kinetic friction. So static friction is the resistance to start sliding. Kinetic friction is the resistance to keep sliding. We said friction, we had 4 laws of kinetic friction. The first 2 were actually things friction doesn't depend on. Even though in our minds we might think it does, friction does not depend, Kendall, on... Remember, one of the 2 things we said friction does not depend on. You're moving the bookcase across the floor, and you're like, I know the best way to do this is to just move it really, really fast, thinking that'll make the friction less. No, it actually doesn't. So friction does not depend on velocity. Friction does not depend on how fast it'd be velocity. And then the other thing was we had the person at the end of the rope of tug of war thinking, I'll just sit down and that'll help us out. Friction does not depend on surface area of contact between the 2 surfaces. We said friction does depend on 2 things. Those were the other 2 laws. Friction does depend on just go skating around your kitchen in those shoes? I think not. Friction depends on anyone? The types of surfaces that are rubbing up against each other. That makes a difference. And then the other thing friction depends on, there's a reason I pulled Kendall around and not Michael. Weight. Which is true on a horizontal surface. We said the better way to think of it is actually different from the way the book describes it. Friction depends upon normal force. And we said the normal force is that perpendicular upward force. From whatever surface that something is resting upon, there's a normal force upward. Well, this is level, so whatever weight bears down is the same normal force coming up unless I start breaking through the floor. So normal force is what friction depends on. So if you have more weight, yes, you will get more normal force. Even on a slanted surface, more weight will be more normal force. Only on a perfectly perpendicular surface. Well, because now the normal force is in the x and the weight is in the y. They're completely separate from each other, right? Components, we're going to get back to those. Anyway, and then we talked about 4 ways to reduce friction. And give me one of those ways. Back to Audrey. Okay, you could use lubricants to cause the surfaces really not to touch, but more to glide against each other. This could involve waxing. Skis would be a sort of like lubricating there. We talked about automobile engines. Another way?
Wheels.
What about wheels?
They make them go faster. If you like push it.
Use them instead of dragging it across the ground.
Yep.
So if Michael is conked out on the ground, well, we need to get him out of the way. He's a safety hazard. Do we drag him along the floor? Do we find a cart we can load him onto and roll him out of here? Right? Put him on a gurney. Right? So rolling an object instead of dragging it, that'll help, right? Using a wheel at all. Though we did even say that within the use of a wheel, there's a way, because there's still friction as the wheel rubs against the axle. We said we could minimize friction there by using
Bearings.
little ball bearings, right? Using bearings or even rollers at the hub of the wheel. So we said lubrication, rolling, just using wheels instead of dragging.
Smoothness.
Minimizing the roughness, making it more smooth. So again, especially with something like wood, smooth it out, or even like cement, concrete can be rough or it can be smooth. Making it smoother would help things to slide more easily. Stage floors are generally very smooth concrete. Outdoors, though, sidewalks, you want it to be kind of rough concrete, don't you? Because otherwise, slip and fall, and attorneys and lawyers and lawsuits and bad days all around. Okay, so but minimizing roughness, sanding down the wood so it doesn't have all that roughness. And then the last way anyone was just choosing better materials in the first place. We go back to skating around the kitchen floor in those shoes. No, soft, fuzzy socks. That's where it's at. All right, questions on all of that? Now, we had two equations then for friction. One was for static friction, one was for kinetic friction. They were pretty much the same equation, just changed a couple of letters in there, and subnotating letters at that, not main letters. Kendall, do you remember those equations?
F, K, equals that letter.
What is that letter?
I know how to do it, but it's like the thingy.
You all have one in your name. Your last name, if it were Greek, your last name would start with, her last name, his first name would start with? Class? Mu.
Yep.
Right? The Greek M. And mu, and we'll notate sub K for the coefficient of kinetic friction, times?
F sub M.
The normal force. There we go. Now, the static friction equation is pretty much the same thing, Kendall.
F and SF equals mu S and force times N.
F sub N, normal force. So coefficient of static friction times normal force. And our homework problems, 10 and 11, dealt with that. We'll get to those here in just a minute. Page 129, though, let's start with problem 7. And go ahead and read that for us, if you would, Michael.
A 16 kilogram ball is accelerated at 17 meters per second squared before it leaves the hand of the shot putter. With what acceleration can you hurl a 12 kilogram ball?
Now, in fairness, the shot put for the Olympic men is 16 pounds, not 16 kilograms. 16 kilograms is about 33 to 34 pounds. Okay, they're not heaving something that heavy. But how many have seen the Olympics? You've seen shot put or maybe a track and field competition or something like that. It's just it's a ball of lead, basically. And they do a spin around and then heave it out. So they get a little bit of motion, momentum going, and then they heave it up. You can't throw the thing, okay? You rip your arm out of sight. So what's called putting the shot. That's what it's talking about. And so we have two different masses here, and we're looking for a second acceleration. Well, we know our main equation for force, mass, acceleration class is F equals ma. But if we have two of these things, we put it together twice to get what, Kendall?
M sub 1 times A sub 1 equals M sub 2 times A sub 2.
Assuming the shot putter is using all of his force for the one, well, let's assume it would be the same force for the other. If the two forces are equal, since force is ma, we can say ma equals ma. So we have a 16 kilogram shot put. By the way, if we did change this to pounds, the other mass would be, well, mass isn't pounds anyway, technically. Pounds is a measure of force, but whatever. It would cancel regardless, okay? So the units cancel. The point is 160, which is Olympic men's. The other one is 12, which I believe is college men's, 12-pound ball. And then the acceleration on the 16-pound shot was what?
17.0.
All right, the question is, what would be the acceleration if you had a smaller? Now, would we expect more or less acceleration, class? We'd expect more acceleration. It's a lighter shot put that he's heaving here, so we'd expect to get a higher acceleration. And when you multiplied and then divided, what did you get for your answer? Let's go back to Michael.
They rounded it to 23 meters per second squared.
Good, 2 sig figs, 23 meters per second squared, 22.6 repeating, but we do round to the 2 sig figs. Did we all get this for number 7? Right, question on 7.
I multiplied 12 times 17 and divided 16.
Oh, you put the 17 with the 12 instead of the 17 with the 16. Okay, gotcha. So you would have got a smaller number than if you assumed the 17 went with the 12, more mass to a smaller acceleration. You were probably somewhere in the neighborhood of 10 or 11. Is that right? All right, questions on that. Let's take a look at number 9. Read that for us if you would, Audrey.
A freight train with a mass of 8 5 kilograms is traveling along a straight and level track at a speed of 92 kilometers per hour. What force applied by the brakes will stop it in a time of 85 seconds?
All right. So it starts by giving us the mass of the freight train, 85 kilograms. And it's going at a speed, or we would say class A, velocity. It says it's straight and level track, so it's going to keep whatever direction it's going. We're just going to assume positive for its velocity. Positive velocity, but notice what it gives us. It's one of those, you see this, like your heart just sinks. You're like, why? Why would they do that to me? 92 kilometers per hour. And it asks for a force. So that's what we're looking for. That is going to stop the train. Stop the train. Thoughts? Final velocity is going to be 0 meters per second. That means this is the initial velocity. And it says in a time of 85 seconds. Well, obviously that's time. We saw a problem like this yesterday, where we know that F equals ma, but we have to find the acceleration. But before we can find acceleration, we got to fix this up. The 92 kilometers per hour, not going to cut it. So hopefully, class, you used dimensional analysis to change it, right? So what's a ratio we would multiply by here, Michael?
3,600 minutes, 1 hour over 3 days. Yeah.
3,600 seconds. There we go. And then Kendall? How many meters in a kilometer? Kilometer? 1,000. So
1,000 meters and 1 foot.
there we go. That'll cancel the kilometers away. So we got the 92 times 1,000 divided by 3,600. I think I did times 3,600. That's no good. 92 times 1,000 divided by 3,600 gives me how many meters per second was this thing going? Anyone?
5.5.
All right, this will save me memory if I do 25.5 repeating. I do 5 on my calculator. All right, so I need to find acceleration first using the formula class. A equals? There we go. So the final is 0 minus what I have on the calculator is basically just going to change to a negative on my calculator. So it's going to be a negative 25.5 repeating. Divide by the time of 85 seconds. Notice our acceleration is going to come out negative. Why? It's stopping. It's slowing it down and stopping it. That's deceleration. If we don't have a negative, that would be a problem. So almost exactly negative 0.3 meters per second squared. Well, now that we know the acceleration class, how do I find that force? Multiply mass times acceleration. So take the acceleration already on the calculator or whatever you had before. You would have multiplied by 85 to get how much force is slowing the train down.
240,522.
Negative 240,522. Notice it's a negative force. Why? Because it's going against motion. The train's going this way, and the brakes are working in the opposite direction. So we should get a negative force here. Putting in a scientific notation with only 2 sig figs, we'll get negative 2.4 E5 and force measured in newtons. And I'm going to have this for number 9. It's a little more involved problem because of the dimensional analysis, finding the acceleration, needing a negative acceleration since it's deceleration. Questions? Questions? Let's understand it now. All right, take a look at problem number 10, and this deals with what we worked on yesterday with friction. Read that for us. Let's see, whose turn is it to read? Kendall.
What minimum force is required to pull a 212 Newton sled at constant velocity if the towing force is horizontal and mu is 0.2.
All right, so we've got this sled, and let's see, sled, here's the surface of the sled, and then here's the runners and the supports of probably some sort of crisscross. All right, so there's the runner, and we're pulling it along the ground, and the coefficient of kinetic friction is 0.23. Now, we're not accelerating the sled at all, okay? So we're just trying to pull it at a steady rate, which means we need to apply a certain amount of force. Well, as you drag something along the ground, there's a force that resists you. What force resists sliding, class? Friction. So if you're trying to apply a force, we'll call this F sub A for the applied force, there's a force working against you, and it's the force of kinetic friction. So if it's working against you, you have to apply the same amount of force as that to balance out the forces. Make sense? To keep moving the object. So the question really is just, what's the kinetic friction? Because if I know how much friction force there is, that's how much force I got to apply, right? How do I find kinetic friction force, class? F sub kf equals mu sub k times F sub n. Now, I know the mu sub k is the 0.23. What about the normal force? Well, it tells me the sled is a 212 Newton sled. If I said that Kendall is a 95-pound girl, is that about right? I can't remember. Give or take 95-pound girl, I'm talking about her weight. If I say it's a 212 Newton sled, class, I'm talking about its weight. Its weight is 212 newtons. But it says we're pulling this along, it doesn't say it's along level ground. But it doesn't tell us how inclined the ground is either, so we have to assume, I guess, that it's level. Anyway, let's assume it's level ground. It doesn't say that in the problem. It should. If it's level ground, which normally we kind of assume, though in Georgia we've got some rolling hills, if there's 212 newtons down, how much force does the ground push up? Equal and opposite reaction.
It says the towing force is horizontal.
True, the towing force is horizontal, but that doesn't entirely, that just means that we don't have a little red wagon, because we don't do sleds down here. If we had a little red wagon, we'd have the handle at an angle. Well, technically that's going to change things. We're going to see that in the next chapter. So to keep it perfect, you're coming down here and perfectly dragging level. That's all that means. But if there's 212 newtons down, class, how much force has to push back up by the ground? 212 newtons has to push up. I'll go ahead and preview this, by the way, Michael, since I said it already. If you pull on the handle and it's at an angle, are you pulling forward or are you pulling up? Yes, both. So you'd have to account for the fact that you're actually lifting. Now, you're not lifting enough to lift it off the ground, but you are lifting slightly, right? Like, for instance, I'm pushing up. Don't actually move. I'm pushing up on his arm. I'm not actually enough to lift him out of the seat, but there was a force upward. What I was just doing a moment ago was barely at all, like a quarter pound maybe, was helping the ground out a little. The ground has to support his weight. And if I lift up a little bit, I'm helping the ground out. Now, technically, it's also carrying me, so that's beside the point. But for him, right, we'd be actually kind of helping the ground out, so to speak, if we lifted at an angle. That's why it said horizontal, because there'd be both X forward and Y upward. Again, I don't want to get into that too much, because that's next chapter. But 212 newtons, that's the normal force. So we should have multiplied the normal force times the 0.23, and how much friction force is there? Therefore, how much force must we apply? And what did you get? Audrey?
48.8.
48.76 rounded off. It is 2 sig figs. So 49 and force measured in newtons. There you go. 49 newtons should have been our friction force. Questions on that? Did we get the 49 or 48 point whatever? Okay. All right. And reading problem number 11 for us now, Michael.
If a force of 26.8 newtons is needed to start a 55.1 newton box sliding over the floor, and if a force of 15.5 newtons is required to keep it sliding at a constant velocity, what are mu sub s and mu sub k?
All right, now this is something that we don't actually have the equipment to do, and we really don't have the time to do because we're a little bit behind schedule of what I want to get done. But you could take what's called a spring scale and connect it to an object. You're familiar with spring scales if you've been fishing. I hang fish from the scale, it tells you how much the fish weighs. Well, if you tug on something with a spring scale, it shows how much force you're tugging with. Okay? And so if we hook the spring scale up to the box, we find that it's sitting here on whatever surface it is, and it starts moving once the force on the spring scale gets to 26.8 newtons. We can also weigh the box easily enough, and we find the weight of the box is 55.1 newtons. So the question is, what is the coefficient of friction between that particular box and that particular surface that it's sliding on? Does that make sense? Every pair of surfaces will have its own coefficient of friction. Well, if I know the weight, again, assuming this is a horizontal or level surface, if I know the weight class, I also know the weight is down, but it's not going down. It's just sitting there, which means there's an action-reaction. What's the normal force? The same thing. So in this case, it's 55.1 newtons. There's 55.1 newtons of normal force pushing up from whatever this surface is, or the floor. It does say it's a floor. 55.1 newtons pushes up from the floor to support this box. Then it says that to start sliding, it takes 26.8 newtons. Well, the force required to start sliding an object is called the static friction. So the force of static friction is 26.8 newtons. How would I find the coefficient of static friction, class? Just divide away the normal force. And so if we take the 26.8 and we divide away the 55.1, hopefully you already did this, I did not, and keep forgetting to grab the answer key. We get what for the coefficient of static friction? 0.4863 rounded to 3 sig figs. Notice unitless, because newtons and newtons will cancel. So it's a unitless coefficient of friction. We do the same for kinetic friction, because once the box is in motion, to keep it going at a constant speed, we find it takes 15.5 newtons. Well, again, the force to keep sliding something, class, is called to keep sliding, kinetic friction. So we take, same thing, just divide the kinetic friction force by the normal force. And again, hopefully you did this, if not, do it now. What's the coefficient of kinetic friction? 0.2813, but again, the 3 doesn't round it up, 3 sig figs, 0.281. Do we get those? All right, if we didn't, does it make sense now? Questions on friction, questions on Newton's laws. All right, got to move fast. Next thing you notice, fundamental forces. Fundamental forces. There's a lot of different forces that can be applied, right? There's forces of pulling something, forces of tugging, forces of pushing, forces of support, all different forces, but there's fundamental forces, forces that are just naturally existing. Nothing special has to be done to make these work. They just work. God made them that way. 4 fundamental forces of nature. The first force we're going to talk about is called the strong force. This is because scientists are not creative, okay? And remember when we talked about quark theory and how everything in the nucleus holds together, and remember we talked about nuclear mass defect, how these protons and neutrons are held together so tightly they actually lose mass through negative potential energy. They're so tightly held together. And so scientists realize, well, electromagnetic force alone, quark theory kind of is based on positives repel, negatives repel, positives and negatives attract, right? But that doesn't fully explain, because then the gluon was a theory of they say basically this: there's got to be a force so incredibly strong it holds it together when it shouldn't stay together based on what we know about electromagnetic force. Yet, it only acts within that tiny range of the nucleus of an atom. Because if it acted further than that, you would cause atoms to somehow squish into each other, and they don't do that. So there's this incredibly powerful force that holds everything together. We're not sure what it is. I have an idea. What do you think it is? God. By him all things consist. But since they don't want to acknowledge God, they say, well, there's got to be this amazingly powerful force. Granted, God made the force. We call it the strong force. So you need to know this about the strong force, or sometimes called the strong nuclear force. It's what holds the protons and neutrons together. And if it behaves the way they speculate it behaves, it would have to be the strongest of all the fundamental forces by far. It is the strongest of all the fundamental forces. So it's responsible for holding the nucleus together, the protons, the neutrons together within the nucleus, and it is the strongest of the fundamental forces. Now there's another force. This one we know very little about. They just came out with a new edition of the physical science book and they didn't have much to say. I've Googled it, I've looked it up every year wondering, do we know more? We don't know much. There is another force that deals with a very, very, very tiny range, like the strong force, and it's evidenced in different types of radioactive decay, specifically with the antineutrino, because the antineutrino should have some degree, based on what we know of electromagnetism and things like that, should have some degree of attraction to things. Or it doesn't have, it's just this weird unattraction to other things. And it's not very strong, and we really don't know much about it. So really not sure what to call it. They call it the weak force. There are some who speculate it's a type of electromagnetic force, but we're really not even sure about that. By the time your kids are in school, we may know more about this force, but there's a behavior in radioactive decay. They're not sure what it is, so they call it the weak force. Really, all you need to know is responsible for some radioactive decay. And if you wanted to get down more detail, I won't even quiz you on this, but there's a near zero attraction for the antineutrino that they say it's got to be something. We'll call it the weak force. Now, it's not the weakest force, by the way. Even though we call it the weak force, it's not the weakest. It's just a lot weaker than strong, and it's even weaker than the next one we'll talk about. The next one is the electromagnetic force, and this is something we know something about. This is actually more observable. Electromagnetic force. You see two basic words in there, electric, and magnetic, right? Electric and magnetic, charged bodies. So know that electromagnetic force exists between charged bodies. Electromagnetic force exists between charged bodies. Now, there's a really goofy illustration in your book. Do you remember what you saw in your homework reading? There's a guy, he got hit in the head with a baseball. You remember that? It says electromagnetic force. How is that electromagnetic force? Well, think about it. All around the baseball is made up of atoms, right? And so the outside of the baseball is also made up of atoms. But every atom is a nucleus surrounded by electrons. So technically, there are electrons covering the outside of the baseball in a sense. Well, how about his head? His head is also made up of atoms. And on the outside of his face, there is a layer of atoms. And on the outside of the atoms are electrons. Electrons are negative. Negatives repel. So when the ball strikes him, there's negative encountering negative, there's a repulsion, and it bounces off instead of somehow absorbing into his face. It's goofy. But here's what you need to know. Electromagnetic force is responsible for preventing atoms from sharing space. It is the electromagnetic force that prevents atoms from sharing space. The electromagnetic force prevents atoms from sharing space. We're going to talk a lot more about electromagnetism later on this year. In fact, you talked about it a lot already in physical science a couple of years back. Looking at magnets, looking at electricity. We're going to talk about electromagnetic force. And of course, you know like charges repel, opposite charges attract, like poles repel, opposite poles attract, all that fun stuff. Okay, that's electromagnetic force. The last force is gravitational force. Gravitational force. This is the weakest of all the forces. You say, it feels pretty strong to me. Every time I do vertical jump, well, you're past your PE days, obviously, but vertical jump test, gravity seems to have a hold on me, Mr. Desk. It's not my fault. Gravitational force, it seems pretty strong. It's the weakest, though, of all the fundamental forces, because think about it. What is it that pulls you down? A massive Earth that pulls you down. But technically, between Kendall and Michael, it's going to seem weird. There's a gravitational attraction. They're attracted to each other right now. They don't even realize it. But it's incredibly weak. Incredibly weak, okay? But it is an attractive force, write this down. It's an attraction between any two masses. It is an attraction between any two masses. Now, Star Wars fans will appreciate this, but between my hand and Audrey's calculator, there is a gravitational force of attraction. And Audrey starts making her calculator go toward my hand. All right? in theory, if I could make the gravitational force stronger, I could attract the calculator and get it. Unfortunately, things like that only work in Star Wars. But there is technically an attraction. It's just incredibly, incredibly small. It depends, and we'll get to this later, on the size of the masses. Greater masses will have a greater attraction. So, for instance, if you were to go to Jupiter, okay, because it's so much bigger, even though you're not bigger, it's bigger, you would be much more strongly attracted to Jupiter. Even Jupiter and Earth have an attraction. So why don't they attract toward each other? Because there's another body that has a greater attraction. It's way bigger than Jupiter, and that's the Sun. And it's so much bigger than all the other things in the solar system that they all attract to it. We'll get to that here in just a little bit. But gravitational attraction, it's always an attractive force. I remember a teacher of mine having a bulletin board up in her room. Gravity, an attractive force. It's true. All right, gravitational attraction is an attraction between any two masses, but it is the weakest of all the fundamental forces. Tomorrow, because we're not going to be able to get to it today, we're going to talk about planetary motion, the movement of the planets. But before we get into that, quick history lesson. There's a little bit of a brief synopsis of this in your book. There was this idea, the moon clearly goes around the earth, right? And I don't know if you've observed this or not. I've noticed it as well. I take walks in the morning, and Venus is the brightest star in the sky, typically. And I noticed that Venus moves in its location relative to the night sky. Well, people made those observations before, and they just assumed these things are going around us. They're not. But that belief was widely supported years ago. You've got to note this guy's name, if you will, Ptolemy. Ptolemy theorized or speculated that the earth is the center of everything. Well, in a spiritual sense, it is. God's plan for mankind, God's care for the universe, all centers around this one tiny little planet we live on. But everything doesn't center on this planet, does it? But that's what Ptolemy thought. There's even a little picture there, a diagram of what Ptolemy proposed. There's these different layers or spheres of the universe. Interesting, at the edge of everything, holding it all together, was this unknown force, Ptolemy said, called the prime mover. Hey, I've got an idea. God, who keeps everything going. But again, man doesn't like to accept the idea of a God because that would make him accountable to a God. They don't want to accept that. But Ptolemy proposed what's called the geocentric view, or the geocentric model of the universe, that everything went around us. Even the stars up there in the firmament, they're on the outer layers, if you will, of the universe, but everything's kind of around us. And that's obviously not true. There was a guy who came along later who said, actually, based on my observations, everything seems to be going around the sun. And of course, he was excommunicated from the church and castigated by others and rejected and scorned because how are we not it, right? But it's true, right? And this guy's name was Nicholas Copernicus. And it was groundbreaking. No one liked to propose new ideas back then. We're going back to the Dark Ages at this point when Galileo proposed the idea of gravity and the invention of the telescope and different things. And he was rejected. And new ideas just largely scorned by the church. But Copernicus was right. And he said, hey, everything's actually going around the sun, except for the moon, which goes around us. And we call this the heliocentric model, or the heliocentric view of our solar system. And obviously, it's been confirmed at this point. It is correct. We'll talk more about how all the planets are going around the sun in our lesson tomorrow. For homework this evening, need you to read over pages 121 to 125. Read over pages 121 to 125. 121 to 125 on pages 128 to 129. Answer questions 21 to 24. Pages 128 to 129. Answer questions 21 through 24. And we'll get into Kepler's stuff tomorrow. All right, have a wonderful rest of your day, and you are dismissed.